All right, super nerds, let's dive into one of the most important ideas in chemistry, Le Chatelier's principle. So, by the end of this, you want to be able to explain Le Chatelier's principle and a system's response to it at equilibrium. Okay, and you'll know you can do that when you can look at a system that we have and predict how it will respond to certain changes. So this is your vocabulary for the lesson. If I can just get you to pause the video here and write this down so you've got it to refer back to, particularly Le Chatelier's principle. Equilibrium, you've probably said a few times by now, but Le Chatelier's principle, if you just write that down, just so we've got something to refer to as we move on through our lesson. So, chemical equilibrium. Here we have two systems. One is a closed system, so energy can enter and leave, but matter cannot. That's this one down here. Energy can go in and out, but the matter's stuck there. And the other one is an open system, and there's no equilibrium here, okay? So the forward reaction will not equal the reverse reaction. And here, the forward reaction will equal the reverse reaction, and that's rate of reaction. And that's because as the matter escapes, new matter is then... So as this evaporates, more of this liquid here will evaporate as well. So in an equilibrium, concentrations are unchanging as reaction is still proceeding in equal rates backwards and forwards. So we see this here with this graph, and we'll see this graph so many times. Here we have the forward reaction, and it starts off really fast, and then it slows down. Here we have the reverse reaction. So this is rate of reaction against time. The reverse reaction will speed up until it is moving at the same rate. But the concentrations is a little different. So amount or concentration. We have the reactants up here. We start off with a lot of reactants. That makes sense. And after time, that stops changing. It stays constant. And as that happens, you would expect the products to stay constant because reactants are used up to make products. We see where these graphs correspond. So the products increase until it stabilizes. And that's because the forward reaction and the reverse reaction are happening at the same rate. So every time this starts to raise a little bit, this one will sink and then go back up, and it'll do this sort of a line. If we measured it finely enough, we would actually see that it is, up and down a little bit. But it makes a straight line to the best of our ability to plot these graphs, and that's when equilibrium has been achieved. So the rate of forward reaction equals the rate of reverse reaction. The concentrations are constant, but not necessarily equal after equilibrium has been achieved. So let's have a look at Le Chatelier's principle. And Le Chatelier's principle is if we introduce a stress, the system will move its equilibrium position. So that's the ratio of concentration of products to reactants. It'll move its position to minimize the change or minimize the stress. So if we change the concentration, if the concentration of a reagent increases, the equilibrium position will shift to use it up. So if we look at this one here, we've got N2 plus 3 hydrogens gives you 2 ammonias, and this is a negative enthalpy negative, so exothermic reaction. So if right here we inject a bunch of ammonia, right, we increase the concentration of ammonia, and all of a sudden we then start to see the concentrations of ammonia and hydrogen, which are the reactants, decreasing until we find a new straight line. Sorry about my drawing there on the graph. A new straight line. And we see the concentration of ammonia increasing. And this is until it finds a new straight line. So a new equilibrium is achieved just here. And this is all to counteract this change here, this increase in nitrogen gas. So as the nitrogen gas increases, then the ammonia moves up to use up the excess nitrogen. If the concentration of a reagent decreases, the equilibrium position will shift to make more of it, right? To increase that. So what happens is if we take some ammonia out, then it will start using up the more hydrogen and nitrogen to increase the production of ammonia. This is actually really useful in industry if we're making ammonia. If we're able to extract the ammonia, this equilibrium system will just produce more. And so that's a way we can manipulate it. So if we change pressure, we're going to stick with the ammonia reaction here. So let's have a look at this one here. If the volume increases, by the way, so if we increase the volume of a vessel, So pressure change and volume change are the same thing. If we increase the volume, the pressure will decrease. If we decrease the volumes, if we squeeze it shorter, the pressure increases. So they're inversely proportional. So if pressure increases, the equilibrium position is going to move to the side with the least gas. It's important to remember it's just gas, moles, and this reduces the pressure because a liquid can't be compressed, right? So if we increase the pressure here, okay, and that's what's happening. You can see the concentration has gone up on all of them because as we increase the pressure, the volume there has changed. So it's moles per volume. So concentration increases. That's what an increase in pressure looks like. So we increase the pressure. As the pressure goes up, ammonia increases and nitrogen and hydrogen decrease. And that's because we have 2 moles of gas on this side and 4 moles of gas over here. So if we increase the pressure, it'll shift to the right-hand side to make less moles of gas. If we decrease the pressure, the equilibrium position is going to move to the left-hand side and to produce more moles of gas and thus increase the pressure. So if the pressure goes down, the nitrogen and hydrogen concentrations, remember that's square brackets means concentrations, will increase while the ammonia concentration, will decrease. So temperature change. Now, if we increase the temperature, the equilibrium position is going to move to favor an endothermic reaction. Okay, reactions are all either exothermic or endothermic. Reversible reactions, we can move them from the endothermic direction to the endothermic direction. So if we increase the temperature, this means we have increased the amount of energy in the system. It will move the reaction or move the position to favor the endothermic side, and because this will absorb temperature, right? So it'll absorb some of that energy, and it will lower the overall temp. It won't go back to what it originally was, but it'll move to reduce that stress. So, over here, this is an exothermic reaction. So if we increase the temperature, pause the video and think, so this is producing energy, so pause the video and write down, just have a guess, which direction you think the reaction is going to go. Alright, I'm assuming you did as you were told. So if we increase the temperature, nitrogen and hydrogen concentrations are going to increase as temperature's gone up, and the ammonia concentration will decrease. And that's because exothermic reaction produces energy, so you want to move it to the endothermic side to absorb energy. If we decrease the temperature, the equilibrium position will move to favor the exothermic side. And this will counteract the temperature decrease, increase the temperature, we'll get more ammonia. As the temperature goes down, we'll get more ammonia and less nitrogen and hydrogen. This is actually really interesting. Where this causes a problem in industry is this reaction only happens at high temperatures. Otherwise, it's too slow a reaction. But if we raise the temperature too high, we won't get enough ammonia. We're only going to produce nitrogen and hydrogen, and that's what we're starting with. So we have to run this at a moderate temperature. It's a bit of a balancing act. If we increase the temperature too much, we won't produce enough ammonia. But if we decrease, if we don't have the temperature high enough, there won't be enough energy for the reaction to happen in the first place. So this reaction is usually done at about 5 to 800 degrees Celsius. Here's just a quick table that is a summary on what happens with each of the changes. So if you need to just screenshot this or write it down, it's just a nice little summary as we move forward. I hope that made a lot of sense. If it didn't, if you have any questions, put them in the comments below and we'll get back to you as quick as we can. Don't forget to subscribe so you can keep up with what we're doing. Hit the bell if you want to get a notification every time my head's going to pop up in a video. And yeah, thanks for watching and we'll see you next time. Bye now.